Hello, Marius. Hello, Bruno.
Hello, everyone.
Je te dérange pas?
Juste un séminaire. Désolé, on passe plus tard. D'accord. Excuse me, can you hear me?
Yes, yes.
Good. So it was a silence just because people don't know things.
Yeah.
Bruno, I cannot hear you.
But is Bruno saying something?
He opens his mouth, I see.
Yeah.
So can you hear me now?
Yeah.
Now
Yes,
Okay.
yes.
probably the level is too high a bit. It's kind of
And now it's better.
better.
Yes.
Even I can
very-
put it lower.
No, that's okay.
No, it's good.
Exactly
Yeah.
okay.
Okay. Yes. And so my question, can you see the screen I shared? So this
Yes.
definition 1 point. Okay.
Yeah.
Then everything works.
So now the bottom line is definition 1.2 to machines UV is.
Yeah. Okay. Great. So I'm happy. So you were talking, I was talking back, not being aware that nobody could hear me. So sorry if I was impolite. So I'm very happy that still people came after previous lecture. And so I will just
It's a bad sign because people don't understand what you said last time and forget everything and want to hear a new. But
yeah, but I like to hear the same lecture.
yeah, okay.
Yeah, I
Okay.
promise to tell a bit
Then
more.
probably we can organize one
But
more after a few weeks.
Yeah, yeah.
I hope I will understand because I missed the previous lecture.
Yeah, I will explain from scratch because it's the only way I mean, the memory of everyone forgot some part, so there's no choice that, uh, and also there were mistakes in my previous talk. But okay, let us start. So what is the question? So we will speak about key agreement. It's a problem in cryptography, and there is a big conjecture key agreement exists. And uh, I cannot hear you, Peter. I see your mouth, but so there is a big conjecture key agreement exists. And the question is, can we make equivalence with some problem in Kolmogorov complexity? And so there was a more or less clean version of this published by Mazur, Liu, and Paz 2 years ago, 2023. So it was paper from Fox. And so it's a long paper, 45 pages, and it has two results. One about, it has also a result about one-way functions, but I didn't read this result. It's like smaller result, and I read it together with Bruno Love, and Milovanov at some point was also involved. And but he told me let's not bother with one-way function, so I still need to read it. But for the other part, it was connected to the problem with Marius on short lists. And technically, I knew everything what was happening there. So there was a plan to make a short paper that the first result could be understood by many people. So, and now I wrote a paper and I made many versions of the proof. And now I think I have everyone voted on the same proof, like Marius and Bruno Love. So I will present the proof and hopefully without any technical problems. I mean, all mistakes, they were small except the definition of interactive complexity, which Sasha immediately pointed out that was something weird. Okay, but let's now start with saying what is key agreement protocol. So there are two players, Alice and Bob, and come on. Yeah, so here is Alice. I put A here, and here is Bob, and they both receive a number n. So that's one input. And the goal is that they both output their version of secret key, which is hopefully equal. And in order to obtain such a key, they exchange messages. So there is a protocol that they both read and write. That means that in turn, they send a string to each other. And at some point, they stop, and then they have a special output tape where should be the keys X and Y. So yes, so that's all there is to say. So so A and B are probabilistic algorithms that receive n, perform a dialogue, and output a string. And of course, the idea is
private randomness or public randomness.
Private randomness. And the idea is that a time-bounded Eve who sees n and the protocol cannot know what is x. So with high probability, x should be equal to y, and with high probability, time-bounded Eve knows pi and n and cannot tell what is x. So yeah, so when I say protocol, we will almost always we just need the mapping n from n to pi xy. So pi xy are random variables that depend on n. But we call it a protocol if there exist such underlying algorithms A and B. That in this way, this B works. So we say that protocol has agreement alpha if probability of x being equal to y is at least alpha, where alpha is function of n. And then we say it's epsilon secure if there exists probabilistic polynomial time, if for every probabilistic polynomial time algorithm and large enough n, algorithm on input n and pi, probability of producing x is at most epsilon.
So for example, there is nothing bad. It's not violated if Eve can guess, I don't know, the first half of x. Just exact reconstruction.
It must
of x
exactly the full string. So it's a quite strong requirement. And
quite weak, I would say. You can have a lot of information about x, but not x.
So for E we ask a lot. Okay, and then there is, of course, we say that it is time bounded, so it is t time bounded. So if computation used by Alice is order t of n, and computation by Bob is also order t of n. And so a key agreement protocol. So this is just how I define protocol. And then so protocol is key agreement. And so if it has, if it is polytime bounded, so its runtime is at most polynomial in n. If the agreement is 1 minus negligible function, and if security is also negligible. So let me write it. If it has runtime n to the power of 1, has agreement 1 minus 1 over n to the power omega of 1. So omega of 1 is just any function that's not bounded by constant. And is 1 over n omega 1 secure. And so agreement is better than 1 minus 1 divided by any polynomial. And same for security. Okay, so and so the conjecture is that K agreement exists. Or I don't know, the question, key agreement exists. So I will write it in short, key agreement exists. So now we want to state an equivalent problem in terms of Kolmogorov complexity. So then I will define for this interactive Kolmogorov complexity, and it will be a promise problem. The equivalence will be promise problem is in the class IOBPP. But I will change this class a little bit because this is a very fragile class regarding the definition. But okay, so let's do step by step. So first step, let's define interactive complexity. So, so here we will have two Turing machines, U and V. And so they they both get a program. Let me write it again with a bit more space. So there are two Turing machines, and they so I will define what is the interaction if U has program A and V has program B. So it means that there is a tape on which A is written, and V has an input tape on which B is written. So they also have, so this is a read-only tape. Then they have a communication tape, so on which they can both read and write, and they both read and write in turn strings. So, and when they write a string, that they say, now my reply is finished, and they write some special symbol to indicate the end of the string. And then they have a private output string on which two strings appear, X and Y. So at some point they halt. And so they're their output tapes. Okay, so this is the computational model. So just plain it doesn't matter. Everything will be up to logarithms. So this is a communication tape. And so when the machines halt, we will see a list of strings pi on the communication tape and 2 strings x and y on the output tape of the machines. And so we will write the output, so interaction of VB, we will say that it's defined by a triple x and y. Just a triple, same triple that we get from protocol. Okay, everyone is already very tired. So it's because it was already clear.
No, so we are looking at definition 1, 2, and we don't see why. This is kind of strange for us.
Yeah. So there is definition Y, and now I explained what means interaction of programs A and B on machines U and V.
Yeah.
And so this interaction creates a triple. And we want to know what is the minimal length, the sum of lengths A, B, that create a certain triple pi XX. So we will always need x equal to y. That's why I didn't add the third argument.
Bruno, are U and V deterministic or probabilistic now?
Deterministic.
Uh-huh.
They're standard Turing machines, just with more input tapes and communication tapes.
Okay.
A little bit more complex.
Mm-hmm.
But that's strange. Last time you say something like you want to have after the communication, whatever it is, you want the machine U to produce X and machine V to produce Y. And this sounds reasonable. But now, strangely, you care about pi, which seems to be just a technical communication thing. And you assume that X is equal to Y. And this is looks strange because just the entire idea was that we want to separate information for X and Y, and if we put all together, we can produce X and Y and whatever we want.
I don't understand your question. I think the idea is to look at on protocols pi, such that A and B would produce the same string X normally.
No.
The definition 1.1.
We want to relate this with the previous definition, but last time it was kind of general definition of communication interactive complexity of a pair. So we need to produce X on one side and Y on the other side, and we need how many bits we needed for U and V. This looked
no,
like a very
I think I gave a bad definition, but it was not bad. Your memory is also there's error on both sides. So in previous talk there was indeed a pi inside the definition, but I said it's not important how we divide the different parts of pi. And this was a mistake. So pi is a list of strings, and we do care which strings are sent by Alice and which strings are sent by Bob. So the odd strings are sent by Alice, even strings sent by Bob, or U and V. It doesn't matter. You understand me. It's because I had a wrong definition of key agreement protocol, where Eve does not know who sends which bits, which was a wrong definition, and then I used the wrong definition for interactive complexity. So, but now it is clear. So in turn they send bits.
Don't you think that the notion of interactive complexity, as I thought you introduced it, just of a pair XY as a minimal length of A plus B, which produce this pair, is interesting in itself? It looks to be very natural, and I thought it was a great achievement in your previous talk. Maybe I misunderstood everything, but...
Yeah, if I remember well, in the paper of Ball and the other guys, indeed they have pi xy.
Yeah, indeed. Yeah,
but it's a simplified definition, which is it's adjusted to the proof.
So
yeah, you can have a triple,
pi
but
also.
yeah.
But then it's very sensitive to the details of the working tape, because if you are interested in the finite state of the working tape, or all the actions on the working tape, or sequence of messages, what you use by pi?
So in the paper, machines alternatingly send single bits. But I think you can have strings as well. It doesn't matter. So what is important is how we measure the time. So we say that the machine can calculate and then send a string and goes into an idle state where he cannot do anything. And then the other machine is working and goes to an idle. So the machine also has work tape, which I forgot to say. So a work tape has its own private work tape.
But if, let's say it again, if pi is a common tape, then, for example, is it possible that the machine just erase everything about after they work and get zero there?
No, so it is one directional tape, sorry. Yeah. Yeah, good. Sorry, good question. Yeah. So if a machine writes something, then it cannot be deleted anymore. So one directional tape.
Sasha, this is not a common tape. This is a communication tape. It's one way, and this is just a sequence of messages separated by commas. That's what pi is.
Yeah.
Yeah. So it's sequence of messages, and they should send them alternatively.
Yeah.
Okay, still. So maybe someone can explain intuitive reason why we add this pi there.
So that the machines
Sasha, what I asking? Why we add pi to the
well, it's very strange. So we want to produce x and y, and pi looks like a technical thing. Just machine agree on some language of what they do, and.
But it's not technical. The opponent sees pi, Eve sees pi. So if we want to characterize the work of the opponent, then...
Okay, but it doesn't measure... somehow you want to measure the complexity.
Yeah.
You know, if you think about this future use, that's okay. But still, it's natural to have some definition which has independent complexity meaning. And in this case, it looks a bit strange to me. But if there is no explanation, okay, but still, we should continue.
Sasha, be patient.
No, and it will not be explained later, I guess.
No. So Sasha is right. So there is a complexity notion in the paper so that we can get characterization, but we can criticize this characterization. It's indeed... I'm not sure if this notion is natural in itself, but also there is
for
this...
example, why cannot we just give A and B to you, and then you will produce just simulate all the exchange by itself?
Yeah. So because we require in this definition that U produces the strings on the odd positions and V produces the strings in the even positions. So pi is a transcript of what everyone says.
Yeah.
So we have a similar...
Then it doesn't deserve the name of complexity of a pair, but okay.
Yeah. So there was this notion of online Kolmogorov complexity, like of odd complexity. So what is the odd complexity? What is the complexity of producing the odd bits in the string if you get the even bits after producing each odd bit? So the online complexity. Yeah. But this is the same notion, except that there is an additional output tape. So it's not only the, so then we can look to the sum of odd and even complexity. So if X is the empty string, then it's precisely sum of odd and even complexities if pi consists of single letter words. And so this requirement is in original paper, that pi consists of single letter words.
No, so there is another notion of complexity. Imagine we have a sequence of messages, of strings, and then we want a program which predicts next string given the previous one, but for even string it should be the one program, and for odd terms it should be another program.
Yes,
and then
exactly.
we just count total size of these two things.
Yeah.
And this is just the same. And the difference is that here we care also about some X, which should be private output.
Yeah, exactly. So for this notion, we know, for example, that interactive so there is also a time bound. Let's say that it's infinite. It doesn't matter that. And so then Ci pi is some of online complexities, for example, odd and even complexities. Yeah, so then in this case, so let us write what is just said. We have that the interactive complexity of pi, an empty string, is bounded by 2 times complexity of pi plus O of 1. Because if we have a program that produces all of pi, we can give it both to Alice and Bob, and they can respectively output the even and odd strings. So it's clear because there's some unhappy faces. So Andrei.
Okay, let me say how I see this. So first, imagine we have a kind of string divided by answer and response and answer.
Yeah.
And then we can naturally define the complexity of answers, the minimal length of program which produce correct answer to a given response sequences.
Yeah.
So it's kind of conditional complexity of answers given response given questions. Given questions, but it's online in the sense that not like in conditional complexity. We have one question and one response. We just have first part of just a sequence of things.
Yeah.
This is a kind of conditional complexity which is split into many parts. For example, we can try to predict odd bits given all the previous bits, and don't care who produces these things. This is kind of complexity. And also we can compute the complexity separately, the complexity of odd bits given previous even bits, and the complexity of even bits given previous odd bits. And you proved that the sum of this complexity can be bigger than the total complexity, which is kind of
by linear term.
Complexity of pairs theorem doesn't work anymore. We can have a bigger thing for this. The sum can be bigger.
Just a moment. So I don't understand what is written. What you write there is not clear to me, right? So just as it is written, it's not clear why this factor 2, because you didn't, the tape contains both, the output tape contains both what the A writes and what B writes.
Yeah.
So,
but the tape is one that.
Then is it not enough if just we read what A writes, and that could be already that could be just complexity of pi without any ignoring what.
Okay, Peter, let me try to explain you without this formula. So we have a sequence.
Yeah.
And we want to define the conditional complexity of odd terms given previous even terms.
But there is nothing about this written here on the
No,
screen.
it's not written, but believe me, it's
So
what you want to say.
So what you are explaining is what you are explaining is then your idea of what should have been written.
No, so there is a notion of interactive conditional complexity. So we have a sequence of questions and answers, and they interleave. And we consider the minimal length of the program, which produces the answers given the questions in a dialogue. So for example, questions and answers can be 1 bit. So our program should produce the odd bits given the previous even bits.
I still don't understand. So first of all, we are interested in, so there is no x and y here, only pi.
No, x and forget about x and y for a while. I just want to explain the general idea before
So
x and y.
But then so the result, it is the complexity of both the odd and even bits, or only the odd bits, or only the even?
The complexity is a function of the entire string, including even and odd bits.
But what the but the complexity, or the complexity, it is the complexity of what?
Of the entire string.
So it is the complexity of the entire, so both
string
the
pi,
complexity of both the even and odd bits, right?
No, it's complexity of even bit conditional to odd bits.
Oh.
So the program
should that's one possible
even bits. The program should produce only even bits.
Oh.
And
okay. But the even bits are written by you, and the odd bits are written by v.
Yeah.
So it's
it's like.
So it is an asymmetric.
Here is a sum of two complexities. Here is a sum of two complexities. The first complexity is the complexity of even bit conditional to odd bits in an online fashion.
Mm-hmm.
It's a minimal program that produces even bits given odd bits previously.
Mm-hmm.
So it should be able to sustain the dialogue with the given even and produce the odd bits, even bits when the previous odd bits are given.
Yes.
And we take the minimum. We also take another minimum.
The minimum over all possible computations of this kind.
Not all possible computation. We have one string, and we take minimal length of the program, which can do this for this string.
Oh, you mean that the odd bits are given, and then
when we measure complexity, like conditional complexity, usually we measure complexity as a function of condition and string.
Yes.
And here we have the complexity is a measure of the entire string, including odd part and even part.
Oh.
But okay, can I just?
But it is.
Wait a bit.
But it is conditional on the odd parts.
Yeah, so there is the complexity of producing the even part, getting the odd part from external.
Yeah, okay, that's...
And also, we can have a complexity of producing the even part, given the odd part.
Okay.
And of course, if we have both these programs, we can just run them together and produce the string entirely.
Yes.
So the total complexity is bounded by the sum of complexity of even conditional to odd and complexity of odd conditional to even.
Okay.
And what is important, and what Bruno proved many years ago, is that unlike unlike the complexity conditional theorem of complexity of pairs, here we don't have the inequality. It's possible that complexity of string is smaller, significantly smaller, than the sum of complexity of even bits given odd bits and complexity of odd bits given even bits.
Mm-hmm.
This is what was as a different old story, but I think this is the notion of interactive complexity. And so here we just consider this minimal A and minimal B, which do these things for pi. So if we don't have X in this definition, it will be just the minimal sum. It will be the sum of complexities for interactive complexity for X and interactive complexity for Y. And here, what is happening, for some strange reason, we add additional thing that after all this dialogue, both machines can produce some X. It's a kind of strange. So we can consider other natural notion. We just have a pair X and Y, and we want a minimal programs which can produce them together, which can produce X on Alice's side and Y on both sides, with minimal programs.
But you must also produce this pi.
Pi. Yeah. No, this is combination of two things. There are two natural notions which I understand. This is interactive complexity of even and odd messages, and also an interactive complexity of a pair AB.
Yeah.
And it is just can be studied without any time bound, and then it's kind of Kolmogorov complexity interesting notion, and it could and should be studied, I guess. But here they are combined somehow, this interactive complexity.
Sasha, yeah. I think that actually this is the same. So I don't see also why he writes in this way. So if Alice U produces X, then she can write it also on the communication tape. And then Bob also knows that X. So we just can concatenate P and X and just consider...
No.
Why not?
Then the problem, if they exchange the messages X, then the second partner, Bob, has a trivial task. He can repeat the message. So it's not like you say.
No. In the complexity notion, the messages are fixed. So when we design the program, we should understand that our communication...
Sasha, say it again. I don't understand you. Say it again.
No, we cannot define what one... we cannot replace this definition by definition of a sequence pi extended with two messages, two messages XX.
Sasha, not two messages, just one of them, X.
But then you don't take into account the necessity for Bob also to produce X.
No,
from pi.
I take into account. Sasha,
pi is fixed. You cannot change pi by writing more on the communication tape.
No. What Koli is saying, that maybe we can define your notion just as an interactive complexity of a longer sequence which includes X after the end of pi.
Right, exactly.
Because when we add X after the end of pi, we just require that after all producing pi in an interactive way, Alice is able to produce X.
Yeah, but then Bob knows X from the messages.
Then it's a weaker thing, because in this definition, Bob also should be able to produce X knowing only pi. And you don't take this thing into account.
Yeah.
Wait. There is no problem for Bob to produce X.
In your setting, there is no problem.
but here Bob needs to think. If X is a random string, then both Alice and Bob, independent of pi, then both Alice and Bob have to hard code this X. Okay, and so we were checking some random properties. So here I need to make some changes. So it will be 2 times complexity of the pair plus of 1. Well, plus, plus of 1. So note that we don't need...
Wait, this is machine dependent U and V. I think my claim was that for all U and V, there are other U prime and V prime, such as interactive complexity with respect to U prime and V prime of Px is at most normal complexity. That was my
No, as usual, you want the prime UV pair UV to be optimal. So actually, U and V are universal things.
I see.
Yes, and also we require
so
the time bound.
Peter, is it clear what he is doing or not?
No, well, it's a complicated definition, so it's not.
that's a problem.
It's still not clear, frankly.
So, well, you should think about U and V as politicians that have to make some act like in a theater. So they perform a dialogue, but they should keep some secrets. And then is the question, how much do they need to remember? Let's say actor with secret.
Well, at this point, let us see, where are the secrets? So they write on this tape, right? And so basically, so they exchange messages, right? Essentially.
Yeah.
They exchange messages, and then so there's
so you complexity. Want to program them so they produce a given exchange messages, given sequence of messages, and also both produce some X after this exchange.
Okay.
So the more general things, it would be to require them to produce X and Y after this exchange. But
I understand. But the complexity is you are interested also in what are these messages and what is this X. So the complexity is all this, right? Okay, and I mean, now I understand what it is. I mean, at least the definition. I understand that you didn't enter this conditional complexities. It's just this.
No, the conditional complexities is somehow hidden in pi. There is each politician has to produce his answer hearing the answer of the opponent. So it's kind of a conditional.
I mean, that's the
interactive.
That's simply the condition built into the protocol. Yeah.
Kind of, but.
Yeah. Okay. So there is this. I guess I understand the definition. I mean, now let us see how about this inequality, right? So, but then I don't.
Inequality is more or less trivial. If you have programs for Alice and Bob.
Yeah.
If you have a program which produces pi and X.
Yeah.
Just normal program without any interaction.
Yeah.
Then of course you can give it to Alice and Bob.
Yeah.
And they know everything, and they can just make a play, just having a full script in advance. They will know what we'll say at every moment.
Yeah.
This is things. Let me ask you maybe a final question. So, do I understand correctly that you can define the complexity of pair pi x from Alice's side, which is the minimal program which produces pi in a dialogue, and X after, and also complexity from both sides. And what you are saying here is just the sum of these complexities.
Yeah, indeed.
Is it
Yeah,
true?
so we can improve it. Yes, it's true. So what you're saying is that this is bounded, sorry, the interactive, let me erase the easy inequality. So it's bounded by a complexity of pi 1, pi 3, and so on, comma x, plus c pi 2, pi 4, and so on, comma x.
Yeah, but I try to say different thing. Not about inequality, but about the definition. I want to check, you should say yes or no, whether my reformulation of definition is correct.
So we'll have to start here somewhere, maybe like
So
4:30 a.m.
So
we can-
Peter, can you switch off sound maybe? Yeah, he doesn't hear.
Okay, so what I'm saying, that we can define the complexity of pi x from the viewpoint of LS,
Yeah.
which is the
Yeah,
minimal length of program, which produces pi
This-
and x,
yeah, I
having
understand.
the outputs for Bob.
Yeah, you're
and
right.
the minimal complexity from the side of Bob.
Yeah,
And then what you define strangely is just the sum of these complexities.
yeah, indeed. That could also work. It's the same. Because
same.
optimizing A is independent of optimizing program B. So as long as the
Yeah. So you
direction
kind
is
of,
the same.
you just have a sum of things, but optimization is independent.
One like the Thailand to
Okay, so let's go to the next so now we understand what is for the time bound. It's clear that's the total amount of computation step the program can make. So remember, machine U, when it's waiting for a reply, it's in an idle state.
Thank you.
Yeah, so we don't count the replies, but if we count, it's just twice bigger or whatever.
Yeah.
Okay. Again, you are do a strange thing requiring that t is a function. T should be a number, but okay.
Yeah, but otherwise I have to write the arguments all the time. It's impossible.
No, you're wrong, but okay, let's do it like this.
Okay, so we understand what is optimal for time bounded. And so we need 1/3 definition, and then we can stay. So we know what is a key agreement protocol. Now we understand what's time-bounded interactive complexity. Now we have to say what it means for a promise problem to be an IOBBP. And so a problem is a pair of sets. So we have all our objects, and there is a yes set, a no set. And so we need a program that that answers when we give it an element from here. It says outside n. And if it gives a program here, it will say outside y. And so the program should never be wrong. And so that means that here it can say whatever it wants. Both answers are correct, both outside n and outside y. But when we are here, we should say outside n, and here we should say outside y. So what means the contrapositive? Whenever the machine says outside y, the element should indeed be outside y. And similar for outside n. So we look at programs that give negative answers and never lie to us. So then there is class IOBPP. So the BBP is a program that lies to us with probability at most 1/3, or probability less than 1/3. But now we have a problem that's an IOBPP, and that means that for infinitely many lengths, the program should satisfy the condition. So here we will have, so in this set, we consider lengths, strings of length n. And so if we only look, so there should be infinitely many n, so that if we only look to strings of length n, so the conditions should be satisfied. So that's what's written here. This is the class IOBPP. It's quite standard
so it's
class.
General notion of separation of two sets by a probabilistic algorithms. And what is strange, usually we require it happens for all n, but now we strangely require that happens only for infinitely many n. Okay.
Yeah. So, but now there is a little problem for this
sorry, and
paper.
what does IO mean here?
Infinitely often.
Oh, okay. Okay.
Yeah.
Infinitely many n in the next line.
Yeah.
Infinitely many n. So there is a small problem because our z are complex objects. There will be pairs pi and x. And so now this, when we model the length, it means we need very fine control of pi and x. If we make a reduction and add things of variable length, we are screwed with this definition. We need to have control over the length. And so I understood that Sasha Shen will listen. So he doesn't like such fine-tuning. I mean, for good reasons, because it's a lot of extra lines in the paper. And so I will use a different class for this reason. So IOBPP, I've seen 20 papers, I checked the definition, but nobody spoke about simple invariances with encoding. So at least 20 I checked, then I stopped. But okay, let's make a definition where we don't have to worry about low-level details of encoding. And so I propose interval IOBBP. And so how does it work? So here we require infinitely many n, so that it works for length of for z of length exactly n. And so here we require z to be correct. Now let us relax this. We want this for z of length close to n, all lengths close to n. So more precisely, we want it for length at most n and at least f of n, where f is small o of n. Just any function, it doesn't matter whether it's computable or not.
No, they're not close to n. You're just between n and something very small.
Yeah,
so it's for
small
most
o
numbers.
of n. So
it's
we
for
require
for most length below n. Yeah, that's what you say.
Yeah. So answer might be wrong for log n or for n divided by log n or smaller. But at least in some reasonable range, answers must be correct. And so if we change now the encoding of z by a linear time algorithm, then the definition remains the same. So if we apply...
If we do what? Say it again. If we
apply a linear bijective function, linear time bijective function, then the definition does not change.
Sasha, what he's saying that this definition of interval IOBPP is less encoding variant. So it's in sort of encoding invariant, this new definition.
Yeah. And so why is it important? We will make a reduction and add things, small things, but of varying size. And if we don't have this invariance, each time we will need to take into account padding and make this fine-tuned for the problem. So, okay, it's not difficult, but also not completely trivial that this invariance happened. Okay, so why is it invariant? So is it clear?
Not just the statement is not for infinitely n. We have something between small fraction of n and n.
Sasha, think that f of n is square root of n. See.
Yeah.
I think it's enough for everything.
Okay, let it be a square root of n. So what? How does it make things easier?
No, it doesn't make the definition easier. It's make it less encoding dependent. So these two lines should hold for all z whose length is in a certain interval. from square root of n to n for infinitely many n.
Okay, it's all strange for me, but I guess that somehow what you really prove in your argument, in future argument, is just kind of reduction between two problems for specific values of n.
Yes.
And this infinitely often is just kind of way to say this in a more invariant way, and maybe so maybe it's even more natural to formulate the reduction for specific n y's just separately somehow for each n. But okay.
I mean, I think it would be easier to understand all the discussion of these definitions if one first would see some kind of specific examples for which these definitions are tailored.
Okay, maybe we should go further and return to this when needed.
Okay. So now this is the main result. So we define a problem. So promise problem has two sets. So small interactive complexity versus big complexity of the pair. And so the claim is that key agreement protocol exists if and only if promise problem is not an IOBPP or equivalent interval IOBPP.
And K protocol exists. What is the quantifier over n then?
In key agreement protocol, there is no, so a protocol is key agreement.
For every n.
Yeah. So it means that, so in the condition, so let's repeat, definition of key agreement protocol, there were three conditions. First, it's polytime. Then there is, for large n, there is agreement.
For all large n.
Yeah. So for all constant c, for all large n, agreement 1 minus 1 over n to the power c. Yeah. So here for large n, that means if n is large enough, agreement should be like this.
Bruno,
yeah.
So I have a problem in understanding this because a key agreement, in the definition of key agreement, there is no T of n involved. But in this promise problem, T of n is involved. So how can it happen?
T is fixed here. You can choose T, and so why T is fixed here, and in the protocol T is not fixed.
Right.
The reason, it can happen because when in the reduction we will apply a padding to pi and x.
So that means
we can make pi polynomial stretch it so that if T is fixed, it has time enough to think what's happening.
So that actually means that the membership of this promise problem in IOBPP doesn't depend actually on T.
Indeed, yeah. So the corollary of the theorem is indeed what you say.
See.
So provided T is bounded by some polynomial and at least large enough.
So let's look at these two sets. Negative set is just says that X has more or less high complexity conditional to pi. Just standard high complexity, yeah?
Yeah. And in the proofs, let us directly use this variant where we say complexity of X given pi is larger than E log length of pi X. So this is true up to scaling of A by some constant, and let's not worry about this constant for now.
Okay, and yes case? when the interactive condition of pi x is smaller than complexity of pi.
Yeah. So,
but why, for example, why cannot we be just in both cases, why the sets are disjoint?
Because E is larger than C.
Sorry?
Because the constant E is larger than the constant C.
Yeah.
No, we have different things on the left-hand side.
You mean that in the second inequality, we have
plain complexity.
We have C without any time bound. And in the first one, we have a time bound and also we have
we have interactive things.
Yeah.
But look, the complexity without interaction and without time bound is certainly smaller, right?
Yeah.
Because we have two programs. We have to, we have to program.
They are inconsistent, these inequalities.
Yeah, there are so many requirements on this definition, so it's very difficult to be and why.
So somehow it says that somehow it says that the condition is really that this polynomial time agent cannot decide whether given pi and x the a and b could agree to produce pi and x, right? Pi.
Yeah. So we need a huge power to understand whether if we get pi and x, to understand whether we can produce it by short program in interactive fashion.
Yeah.
And if we have this huge power, we can break key agreement and vice versa. It's our main theorem.
So in other words, yeah. So if the enemy cannot decide whether we can produce something like this, then we can actually produce something like this.
Yeah. Yeah, this is a funny summary.
But wait, so in theorem 1.4, there is no interval IOBPP, right? That's normal.
Well, it's both, basically the same proof gives both variants.
I see.
What Bruno was saying, that if we speak about just IOBPP, then it's very important how we encode this pi and x in YC and
I see. So the statement is interval IO is more natural in a sense.
It's more stable because without this interval, it's even not well defined because we don't specify the encoding.
Yeah. So in the paper, I do like everyone and specify the encoding. But for the seminar, it's let's not do it. It's too many details. It would take forever.
Mm-hmm.
And by the way, a great help if you use single bit messages, then you don't have to worry about encoding strings.
But so that's still we have encode pi and x.
Yeah,
so
the pair encoding.
We need to add something to separate them. Still, so it's up to a we don't have a natural up to a single bit encoding.
Yeah, exactly. Okay, so now we kind of hopefully understand the statement. And so it's the first part of the talk, and we will prove the two implications. So it's the goal. And so we will prove the negations of the two criteria. So we will say that key agreement does not exist. So we can break all. So if we have protocols to break all key agreement protocols, then promise problem is in interval IOBPP and vice versa. So if we can solve this promise problem, we can use it to break protocols. And so first direction is the forward direction. So if we have breaker for every key agreement protocol, we can solve the YN problem. We can give interval IOBPP algorithm. So, and this is what I tried to explain previous time, but only Sasha Kolochinsky was alive at the end of the talk.
Sorry, I didn't quite understand. So when you say we can solve the YN problem, I still don't understand. You can solve it for certain specific YN or for arbitrary YN.
Yeah. So if we can solve it for just okay, I forgot to tell. So
many
the YN
intervals. If we can solve it for infinitely many intervals, then we can break key agreement for some length, for infinitely many length, which is by definition what means to break key agreement.
Yeah.
Key agreement by definition should work for all length. So breaking it means breaking it for infinitely many length.
Yeah. So okay, but by the way, let us have a look at the problem. So there are three parameters.
So you have this specific YN in right in all this you have this specific YN in
Yeah.
Right? Yeah.
So the problem depends on
those here are defined.
Yeah. So there are three parameters, T, C, and E. And so let us understand when the problem becomes easier. So is problem easier if we decrease T, or it becomes harder if we decrease T? What do you think?
For whom?
For
whom it becomes easier and harder.
Promise problem for an algorithm trying to solve it, I guess.
Yeah. So imagine we have an algorithm that works for a large T. Do we also have can we use it for small t?
The greater t is, the greater is the YCT.
Yeah.
So and the problem becomes more difficult.
Yeah, indeed. So if we make the sets bigger, then it becomes more difficult. And the same for C. If we make C bigger, then the set Y gets bigger. And again, more difficult. And for E, it's the opposite. If E is very small, then N is big. And it's more
decreasing E increases N.
Yeah. So if E is bigger than C plus 1, then we know it is they don't intersect. And so there is a chance to solve it. But if they intersect, so if E is smaller than C, I don't know what's happening between for certain values. I should think, I never thought about it. But if E is much smaller than C, then the sets overlap and there is no chance to solve it. Okay. So now let's look to the first direction. So here are precise bounds for E and C. So for all values of E, C, and T that respect these conditions, the problem is equivalent. It's a corollary of the theorem. But I will not worry about specific values. So now I will assume that E minus C is at least 8. So E is much bigger than C. And T is bounded by polynomial in the proposition. Then I assume we can break key agreement. And under this assumption, let's prove that the Yn is an interval IOBPP.
You have some strange gamma, it should be E or something. Or
sorry, it's C plus gamma. Let me correct this.
Gamma is the difference between C and C.
Yeah.
C plus gamma. So now hopefully readable.
Yeah.
So here is C plus gamma. Okay. And so last time I explained this, and so I explained, we did it by considering one specific protocol. I will say very late what is this protocol. I will tell you what is the algorithm to solve. So first, I will just give into for some version of IOBPP. So here this is easier because it's smaller requirement. So algorithm for so we assume that we fix some encoding of pi x. And so here is algorithm to solve the y-end problem on input pi x. And so first we define parameter n to be the length of the encoding of the pair. Then we do something very strange. We will calculate some hash value by independent hashing. And the length should be c plus 6 log n. It's very strange. We will not understand it till the end of the proof why we add something to pi. And so pi tilde will be pi plus the strings h of x, the hash value of x, and some 1. And so this comes from very specific protocol. I will keep secret till the end of the proof. And so then this augmented protocol, this augmented transcript, pi tilde, will be given to the breaker. So breaker has two arguments. It knows n and the transcript. So the breaker, if it answers the correct x, then we will reply that we are outside n. No, recall, outside n means conditional complexity is small. And otherwise we say outside y. So this is the algorithm. So again, so algorithm gets pair pi x. It checks what is n. It adds a hash value, hash function and a 1. And then gives it to the breaker and it checks whether it gets indeed x. So now the question, what is the breaker is secret still. And what is which protocol is breaking is also secret. But we can already understand up to one little claim why this will be why this algorithm will be successful. So we have to check condition of IOBPP. So let us recall, we will use contrapositive. So here is the definition of IOBPP. So remember that we have to say that if
so we now assume for all sufficiently large n, this is unsuccessful.
No, we prove the positive. So we will prove that this algorithm, even though we don't understand it yet, is indeed able to tell y and n. But I will make one claim.
For infinitely many
for infinitely many n.
Yeah.
But now we need to remember what means successful. And so here are the two conditions. But we will use the contrapositive. We will say, if algorithm outputs outside n, then we need to prove that we are indeed, so with probability more than 1/3. Sorry, so the contrapositive is the opposite, outside y. So if algorithm says outside y with probability more than 1/3, it needs to be outside y for the first condition. And symmetric for n. If algorithm says outside n with probability more than 1/3, we need to prove that we're indeed outside n. Okay. So that's what we have to do. Now let's go back to our algorithm. So first claim, if algorithm pi x is outside y with probability, then we have to see that we are outside y. When does it say outside y?
When e of n pi is not equal to x, if you say in your algorithm.
Yeah. So sorry, I think it should be, I've made a mistake here. outside and E. So that's an easy direction. So probably I forgot to delete after rehearsing. Okay, so we do it. So if algorithm says outside N with probability more than 1/3, then pi x is outside the N set. So the N set, we will use this one, right? Means if algorithm says outside N, what does it mean? That means that with high probability N pi tilde produces X with probability more than 1/3. Then we claim that pair pi x is not in ny, it's on the top of the screen. In other words, we claim that conditional complexity, so that's what we have to prove, that conditional complexity of x given pi is small, smaller than e log pi x. But this is clear.
Just a trivial question. I don't understand this thing about just with probability one third. So if it is probability 1/3, if that's all that you require, then always just tossing a coin would satisfy everything.
No, it's error probability 1/3.
Yeah, that's why I'm saying, yeah. So it's probability 2/3 really. Yeah, okay.
Yeah, but he speaks about the probability of error, and just it's a sequence of contraposition, so we are lost. But let's try to.
No, I can repeat this.
Maybe it's better, because now it looks like completely pointless thing, because you don't say which algorithm, and we are in suspense is not in the 1/3 place. It's just everywhere.
So suspense is I didn't say what is E. I just say that the first requirement, we don't need to know what is E. It's automatic, no worries.
Okay.
So yeah. So if algorithm says outside N with high probability, then we are outside N. And so what does it mean? If algorithms, so we know that C of so if it can guess X with significant probability, we know that complexity of X given pi tilde is bounded by constant. But what is pi tilde? It's the original transcript plus a bunch of random things. So plus and a hash value. So okay. So that means that what can we say about complexity of pi? So the hash function is just a random object. So adding it will not help to decrease the complexity with significant probability. But we also added hash value. This can help us.
And so can now decrease by the length of the hash value.
Yeah, indeed. So now we only know that is bounded by length of hash value plus O of 1. And we have a specific bound for this hash value. It is C plus 6 of log n plus O of 1. Now let us look at the value of E in our set and E. It was C plus gamma. So it should be outside N C plus gamma. I wrote CE again, but it's unreadable anyway. So let's just delete this. So here should be NC plus gamma. And we said gamma is bigger than 8 or 7 or whatever. So we have that this is bigger than gamma plus C plus gamma log n. And so if n is large, we can forget about the log n. We can make it strictly smaller. And so it means that we have proven that pi x is not in n C plus gamma. So it's on the top. Here is, so E is equal to C plus gamma. So it's, so for to
easy part.
Yeah, you just have to know what is NE, that E equals C plus gamma. Gamma is 7 or more, and it's clear. So somebody should ask something. if the
No, I suggest we look at the difficult part and then we confess that we don't understand even the easy one.
Oh, I think no, we should have first small success and then we can continue.
No, wait, we have no success here yet. So
okay.
I don't understand why. So you are designing a protocol, key agreement protocol, and you use that if can break
No,
it, right?
We are designing algorithm to solve YN problem.
Okay, but we assume that the key agreement does not exist, right?
Yeah.
How we use this assumption?
We have to prove two claims, but my claim one is easy and we don't need anything about key agreement. It's automatic. It's also true. So we need to prove that our algorithm is correct. For this, we need to check two claims. If algorithm says outside N, it must be outside N. If it says outside Y, it must be outside Y. We will now prove the first
Bruno,
claim.
What you assume
when
about
you design
say
your
it again. What you
when
assume
you
about
design your IO-BPP algorithm, do not you are you using your assumption that key agreement
use
does
some
not
mystical
exist?
E.
I will use it later, not yet used.
So
what do you
the
assume
proof
now
of easy
about
direction
E?
is not finished yet.
Yeah, for E we didn't use any assumption on E except that it's computable algorithm.
So that means that the easy direction is not finished yet, right?
No, easy
No,
not
I
yet
don't
finished.
understand. Imagine that E is always gives some string which is different from X. Then we will also always output outside Y. It's not what we want, I guess.
Yeah, but now we can so we are checking first requirement.
We're checking only first requirement.
Yeah. I need for second requirement we need to construct carefully E.
Yeah. So we checked one requirement in one direction of the theorem.
Yeah, so it's 1/4 of the work, and I'm checking whether
this requirement involves some mystical E, but now whatever E is, it should be okay. That's what Bruno is saying.
This requirement is true for all N, for all E. It's automatic. It's free requirement.
Okay, let's look on the second part of the first.
Yeah. So then the second half of proposition. So now we want to prove...
Not the second half of proposition, but the second part of the same direction of proposition.
Yeah. So we're proving this proposition.
Yeah.
Okay, so I will delete all this. Yeah. Okay, and here it's slightly more clever. So let us...
because you need some E.
Yeah. And still, I will not tell it for a long, for some time. So what is our plan? So we will prove that, so we will consider pi x, for which we are wrong a lot of times. So we need to consider if algorithm outputs outside y with probability 1/3. So we failed to guess x for a large probability. We will construct E such that it only happens for pi with a very small complexity. So we will prove that this one is very small, this C of pi. And then we will conclude it's too small to be outside YTC. I lied a little bit. I said very small. It's just small enough. So this is our plan. We prove that C pi is small. So whenever interactive complexity is large, and this happens, C pi is small. So this is our plan. So let us define a set, NL, of these strings where guessing happens wrongly with high probability, and complexity is equal, interactive complexity is equal to L. So we say that a pair pi x is in this set if and only if, so condition, so we will say that the encoding pi x must have length n. Okay, let's say length n. Then the second condition is that interactive complexity with time bound c of pi x is equal to L. And finally, our algorithm outputs outside, so outside n, with probability more than 1/3. So these are the three conditions. So let us collect all this special pi x. And now I will later claim that this set is small. So what will be the quantitative bound? So there is another claim that we will need to prove that SNL is smaller than 2 to the power L 1 over n to the power c plus 3. So this is the magical thing. After we've proven this thing, so we will construct E so that this is true. There we need E. And after this thing is proven, we understand that each pair pi x in S cannot be in Y. So S and Y will be disjoint. So let us check why this is true. So, okay, so we believe this. And now let us look to complexity of pi, assuming, so let pi x be in this set S and L. And let us now give a bound on complexity of C pi using the set S. So it will be the logarithmic size of S and L plus 2 times log n, because we need to know the parameters n and L. And actually, so y and s being disjoint for large L is kind of easy. So there are no strings for which CIT pi x is bigger than 3n. So bigger than 3n, and n is equal to the length of the pair pi x. So unless n is bounded by constant, of course, there are only finitely many pairs for which this happens. So we can assume that L is small compared to n. So it's clear, right? Because n will be larger than the complexity of the pair. Okay, Sasha understands.
No, I'm completely lost, but just I want you I want to get some kind of general structure. Maybe you should finish just ignoring my ignorance, and then we will try again.
Yeah. So let's try to. So how can we bound it? So so I assume that pair pi x is in the set S and L. So then we bound complexity in the usual way, right? But here I'm using that L is smaller than n. So this is just a technical hiccup. We can assume it because in our set, L is the interactive complexity. It's always small compared to n, which is the length of the pair. So in our set here, the first condition, n is the length of the pair. So this inequality should be clear. So it's okay? Yes or no, Sasha?
No, I want no. But I want you to continue. I want to understand the general structure before going to the detail.
Yeah. Okay. So
what
now
you are trying to.
Now we use the claim. We use the claim. So we say the size of S is small. So this is bounded by L minus 3 plus C log n plus 2 log n plus, I will ignore the small o of log n. Yes. Now, what is L by definition of S? So know that in the set S, we fixed interactive complexity precisely. So we know that this is equal to interactive complexity pi of x. And then we do some calculations, minus 1 plus c times log n plus more things. Okay, and now we have good news. So what have we proven here? We have proven that interactive complexity is large compared to c pi. So when we flip this, let's change the sign. So we have proven that interactive complexity pi of x is bigger than c of pi plus c log length of pi x. But the length of the coding of pi of x is more than. So we conclude that pi x is not in YTC. Not in YTC. Because interactive complexity is large. So that's
then it remains to prove some claim.
Yes,
and then,
exactly.
Then you need to explain what is E finally, which you hide from us up to.
I've been making you very frustrated, and you're right that we are now. Okay, so we will get E from Hohenstein theorem. Okay, so here you read the protocol. Maybe I should be annoying and even postpone more and first say Hohenstein theorem. So I just want to move something. So let's move it down. No. Okay.
Yeah.
It seems that. Okay, let's do it in parts. Okay, I will later. So Hohenstein theorem. So they say that if A is bigger, so Hohenstein, it says that it says that if we can break key agreement, if we can break all key agreement protocols, then we can break all key agreement protocols in a very strong sense. We can have an if that always guesses the full key with conditional probability, very large conditional to agreement, even if agreement is quite weak. So agreement should be 1 minus negligible function agreement protocol. And so Hohenstein 2005 says that even if protocol doesn't have negligible, 1 minus negligible agreement, but just 1 over polynomial agreement, then we can break conditional to agreement. We can have a breaker that finds a full key with probability close to 1, conditional probability close to 1. Now we only need a weaker version of it. So we will consider, so if A bigger than B, and then key agreement does not exist, and protocol has agreement 1 minus 1 over n to the power alpha, then there exists a breaker that finds key with probability 1 minus 1 over n to the power beta. So note A and B I used. So
that's amplification.
Yeah. Alpha bigger than beta. So it's enough
you
to
cannot
have...
find the key if the keys are different. So it's natural that alpha should be bigger than beta. That is not make sense to ask about. But
You
have different.
So if if Alice and Bob just output random strings, there is no chance to break it. But also they have small agreement in this case.
Yeah.
But if we are, key agreement considers 1 minus negligible probability. Here we just require 1 minus 1 over polynomial probability. And then there exists an if such that E of n pi equals to x with probability 1 minus 1 over beta.
So it's kind of amplification of key agreement, making amplification of security of key agreement.
Yeah. Okay, and so now we understand how to get E. I need to tell you against which protocol it will be used. And remarkably, we will only use it against one protocol. And so in the paper, I call it Levin search protocol. But it's a protocol who assigns high probability to pairs with small interactive complexity. So now finally, here is a protocol. So let me move it. So I will move the screen now so that we can see more. Okay, so Alice and Bob generate two lengths. So they will generate random programs and let them interact against each other. Then they will extract the key and check whether they're equal with hash code. That's the summary. So if they're equal, that will be the two strings. If they're non-equal, they will output empty string. So how do they generate random programs? First, they choose.
Hollenstein is taken as granted, and you now explain to which protocol it will be applied.
Yeah, indeed, yeah. So Hollenstein in 2005. So it would take like 2 seminars to explain Hollenstein theorem if everything goes right. So it's difficult theorem. It's connected to machine learning. I read all of the proof, but I didn't try to check well. So, okay, let's not speak about it. So Alice and Bob, they will choose two lengths, LA and LB, then generate random strings of this length, and that will be their programs. That will be the programs A and B they feed to UNV, the optimal pair in interactive complexity. So then they let these programs speak to each other, and then they obtain the triple pi x y. So they will do a check. They will check whether x equals y. They use hash code of length c plus 6 log n that detects inequality with probability n to the power. So it has collision with probability at most n to the power c plus 6. So if x is not equal to y, they will detect this with high probability. If the check is successful, Bob will send 1. So Alice will send the hash function and the hash value. And Bob will say whether everything is okay. If okay, they output x and y. Otherwise, their keys will be empty strings, which are equal for sure.
And about length of x and y, they don't check anything, just any length is okay.
Yeah, any length is okay. So they run the programs. However, if program runs too slow, so we have a polynomial upper bound on the time in the assumption of proposition. So if this time is exceeded, then Alice will inform it. So it can do by sending a string of this polynomial length, and then Bob understands they can stop. And so this protocol runs in polynomial time. So, but if x and pi are of reasonable length, they can perform execute this program.
They just behave randomly. They take more or less random program of length, some length, A and B, LA and B, and then they just, maybe these random programs will produce the same string. They check it with hash functions.
Yeah,
and
exactly.
if they produce the same string, this is what would be the secret?
Yeah. And if not, secret is empty
Yeah, it's
string.
indeed like Levin universal algorithm.
Because implicitly
or
they are
whatever.
simulating all possible protocols, because their random program can begin with the start of a certain protocol and then contain the random bits. Okay, and so so now note that this protocol has agreement 1, so this will be the agreement, a bound on the agreement.
Yeah.
Because the only way to have different keys if there is hash collision. Okay, cool.
So
we can
but the agreement is we pay for this just to usually we output empty string. This is just the
yeah.
And that's why they agree most of the time.
Yeah. And so we know that there is a breaker. So now we apply Hohenstein theorem. So by Hall there exists a breaker, and by tilde equals x with probability 1 minus 1 over n to the power c plus 5.
So Bruno, you have one
mistake
in the statement of Hohenstein. It's if there is a breaker with agreement 1 over n to the alpha, then there is a breaker with 1 minus.
Yeah, I took contrapositive of Hohenstein theorem, because it's what we know. So he says if there is a breaker that just guesses with small
I mean, it's not 1 minus 1 over n to the alpha, it's 1 over n to the alpha. No?
Let me check the paper.
No, that's how you use it, yes, because now you use it, so you take alpha to be c plus 6.
So, sorry, I'm confused. So agreement is okay, right? And then the theorem says is not 1 minus 1 over n beta secure.
So you want to amplify agreement, yes? From 1 over n to the alpha to 1 minus 1.
No. Amplify security. Agreement is just a little weaker. Yeah.
Yeah, okay, sorry. Yeah, okay, sorry.
Yeah. No problem. Okay, so so by Hohenstein, our breaker guesses x with very high probability. In other words, failing to guess x has very small probability. 1 minus 1 over n to the power c plus 5. Okay, but now our protocol is tailored to simulating interactive complexity on random programs. So let us now consider pi x in our set in S and L. So what is the probability that pi x is generated inside our protocol here? That it appears here when we're running the protocol. So what do we know about pi x when it's in the set? So it's on the top of the screen. We know interactive complexity is L. So what is probability that pi x is generated? What can we say? So in this definition, we have two programs, A and B. Let us call it A tilde and B tilde. So now what is probability that A and B that are generated here? We have AB equal to A tilde and B tilde. What is this probability?
And what is the length
of
A?
So we know that
B tilde.
Yeah. So here we have A tilde and B tilde are the witnesses of interactive complexity. So we know
L,
that
there's L.
Yeah. So this probability, so this happens with probability is 2 to the minus L, but also the lengths have to be guessed right in the beginning. LA and LB have to be right. So it is a little bit less. You have
over n squared.
Yeah, 1 over 3n squared. Okay. So what also do we know? So this is probability that so it is in Sn, so this is a pair pi of x where E is wrong with high probability. This is our definition of set SL. We know that generating, so if S is very big, then there will be many strings on which our breaker doesn't work well. But we know it has small probability of not working well. And so we conclude that S must have small size. So if pair is as an L, we know it's generated with high probability. So let us look to probability. Okay, let's just write everything. So probability that A fails for a given value of n. It is bigger than 1/3 times the size SNL times probability of generating one element inside 3n squared. And we know that probability A fails is small. It is 1 to n c plus 5. Right? So we look to the probability that A fails. Now we can look to the probability, that's the sum that A fails on a specific pi x in S and L over all pi x's in S and L. Right? We apply union bound. So for each pi x, we say what's the probability that E fails because of this pi x. And then we sum over all pi x's in N. Yeah? So probability that it fails on specific pi x is, or maybe it's more pedagogical to put 1/3 here. So here we have union bound times 1/3 the probability of generating pi x in the protocol. Okay, so there are some confused faces. So Andre and Sasha.
So just we are over time, of course, as usual.
Yeah.
But I have a dream, like Martin Luther King. So the dream is that Kolya explained me everything again in next week or after 2 weeks. Is it possible?
In September.
No, I will forget everything.
Okay,
Maybe.
that's good.
Okay.
No, I think
maybe Andrei can do this.
We have to finish.
Okay, just to finish. So we only had to finish the claim. And so now we have finished the claim. So we have proven an inequality, and as an L is small. We just have to move this to the other side. So what is written here, we have to put to the other side. So we have proven size S and L smaller than, so 2 to the power L, so big O to the power L, n squared. 1 over, let me put here. So n squared goes to the other side, but here we have 1 over n to the power c plus 5 minus 2. So this is what we achieved, and what we needed was, okay, I forgot the big O here, but it's not important. We needed 1 n to the power c plus 3. And so we finished the proof of the claim. It means we finished the proof of the second requirement, which says that pi x is not in YC whenever E says x is not guessed with probability more than 1/3.
So, and that was an easy direction.
Yeah. So, well, actually, directions, maybe they're equally difficult. So what's happened in the other direction is that there is a simple philosophy and then just many things that need to be checked and go right. So it's kind of a lot of routine work. So if we agree to skip it, then the other direction could be called easy.
Tash, maybe you understood
people are
something and can
tired and
explain it.
confused now.
Okay. Yeah, I should just repeat. I don't know what time it is. It's
20 minutes past 8.
oh, sorry for that.
Yeah. Sasha, maybe you understand what is happening and can explain it again once.
No.
No.
No, I'm more than happy to explain it again next week.
Yeah. No. The question is that someone should speak with you several times and then understand and produce some kind of.
I can only confirm that there's a text by Bruno and Bruno on archive, and it is surprisingly short. It is only 13 pages long, including the bibliography.
Okay. Have you seen Levin's paper?
Yeah.
Okay.
So
Yeah, but there's no Banach spaces or
I will
something.
try also. I will try to look at it and think about what is happening also. But now I am completely overwhelmed by what is happening. It looks like a miracle from the beginning to the end, and I don't realize
but
why
I suggest we Sasha, I suggest we postpone it not for a week, but for 2 months, something like that, or 3 months.
But be careful. In 3 months, it will be August, and
No, I mean till September.
Okay. No, if it's better than nothing, but so.
But I feel I think I feel the same as Sasha. I'm very deeply lost. It's maybe my fault.
Yeah. No. It's a good idea to have some preliminary exposure like this, but then we need to get and start from scratch and try to understand what is happening again. It's not. It's normal, but
Well,
I just think. Yeah.
I remember that I read. I'm not sure if I read the last version, but the one before the last one. And this part was not so hard to understand. Of course, you have to understand the details of the protocol and so on, but it's not that hard. I think the other direction is more innovative and
doesn't sound very promising, but okay.
No, but I think it's just you just have to read. I think it's hard to tell it in a seminar, but if you just because I think it's like 1 page long. This argument.
Well, the definition took a long time, and so
okay.
You can be angry about maybe I didn't.
Yeah, the rest is. But yeah, okay, sure.
Yeah, so it's 2 pages, the proof, but the problem is that we used a lot of time for the definition. So I thought it would be easy that I didn't prepare very well.
Yeah, but it's a tangle of definitions that you have to understand within a lecture and immediately see it applied. So it's kind of
Yeah.
Okay. So let's just at least I want to say that Kole agreed to provide the explanation in September if no one can do it earlier. This is already a good start, and maybe also he can hear in advance the other direction and also be able to provide to comment on it. It will be very nice.
Yeah.
But and then. Bruno, you planned something for next seminar or what?
No. The plan changed. So you made some analyze in email, which was better than I suspected. So no, there is nothing for next week.
Yeah, then Sasha, you have some plan for next week, or not for next week, about this polyhedron and Hamiltonian path on it.
Yes, but I have to verify what happened.
Yeah, we hear you. You have to verify that the speaker is alive and can produce something.
Yes.
And
I have
also,
to-
you should verify that the proof is correct, and you can explain it clearly if the speaker fails to do it.
But I don't know the proof yet. I mean, I know the idea of
Yeah,
the
but
proof.
it's next week only.
Yes, I understand.
Okay,
But
okay. So just think about this, and if there are some other options.
let me try to verify right away. So I'll just verify and then I'll let somebody know.
Okay. No, there is also the thing which I tried to explain last time, but didn't even manage to start, about how this fixed point theorem can help to produce combinatorial consequences from Kolmogorov complexity. But if it's not that, I think if we have something else, it could be better.
Mm-hmm.
It's the advantage is very easy, but still I think it better to have something more deep. Okay.
Okay,
Then-
yeah, I
then
have to quit.
Yeah. Thank you very much for your efforts, even if they are not very successful. we really appreciate it very much, and indeed the theorem should be studied, and we hope that it will be at some point understandable. But let's try again. Okay.
Okay. Thank you.
Thank
Bye.
you.
Thank you.
Yeah. And Sasha will tell us maybe whether this new Hamiltonian thing will happen. Okay.
Thank you.